Okay, so welcome back. We stopped talking about, we stopped at the part where we were talking about the pipeline, which is the reduced instruction set computer. As you can see here, we have 4 stages, which is the instruction fetch, decode operand fetch, execute, and write back. Now, in this data path, we have 32 registers, and each register has a size of 32 bits. We have the introducing of mux A, where we have the PC-1 part over here, and we have the value of bus A. We have RAA. We are going to talk about all of these now. Now, the data path, as you can see, we have 32 by 32-bit register file, and R0 is always giving a value of 0. All register file inputs are 5 bits and 5 addresses over here, as you can see, AA and BA, which is the addresses for address A and address B. Now, the organization of the data path, as you can see here, the shift right and shift left, it has SH, which is 5 bits, and this is for the shift right and shift left, and this is basically one type of the Braille shifter, and this Braille shifter can do from 0 to 0 cascaded to AA is 32 bits, so we add 32 zeros, so we end up with 64 bits. This is very important in order to implement the 0, 32, 16, 32, and 42-bit operations. And here we have 4 to 1 multiplexers, 74, 4 to 1 multiplexers. Here we have 35, and here we have 32 multiplexers. Now, the right and left control of the opcode select shift right or shift left, as you can see over here. This is explaining the Braille shifter. And in order to provide zeros and to simplify our values, we fill up the values with zeros, as you can see over here. Now, this is also explaining that shifter. Now, the constant unit, okay, the constant unit CS is over here. This constant unit will either select between 0 fill the immediate or sign extend the immediate. So if it is CS is equal to 0, then it will 0 fill. If CS is equal to 1, then it will go for sign extend. Mux A is added to provide a path for PC and PC-1 to the register file for implementing the jump and link instruction. So for the jump and link instruction, we need what? Let's go back for the jump and link. For the jump and link, we need the value of PC to be saved into RDR. Okay, we need the value of PC to be added to RDR. Now, in order to do that, as you can see, in order to do that, we have PC-1 is added over here. It will go through bus A, through the register file, and go back into RDR. Why PC-1? Because remember, if the instruction happened, let's say at PC equal to 100, now at this cycle it is PC 100, here it is PC is equal now to 101, so -1, it will give us 100. So it will reserve our value. Remember, program counter is incrementing every time plus 1, every time plus 1, every time plus 1. So if you want the original program counter that happened here, in this cycle you need to -1. In this cycle you need to -2. Now, to implement set if less instruction, we need this XOR between negative and overflow. Now, this one, the logic provides 1 to be loaded into RDR if RSA minus RSB is less than 0, and a 0 to be loaded into RDR if RSA minus RSB is greater than 0. So it is implemented by adding an additional input to MUXD. As you see over here, we have a new input to MUXD, and this input is 0 filled. Okay, this input is 0 filled with 31 zeros and added as the second input for MUXD. Okay, so this value will come here. If it's RA minus RB is less than RA is less than RB, then we are going to have 1 with 31 zeros beside it. Otherwise, we are going to have zeros with 31 zeros beside it. This is done by having the values as follows. So the leftmost 31 bits is implemented as 0 and 1 if n is 1 and overflow is 0. Meaning, if I subtract RA minus RB and RA is less than RB, then my answer should be negative. Yani if I subtract 3 minus 5, this is RA and this is RB. Remember, the instruction is set if less. This means RA is less than RSB. So the answer will be minus 2. So my answer will be negative and overflow is 0. The other solution is to have the negative equal to 0, but we have an overflow. So when you subtract two big numbers from each other, you get a positive number but with an overflow. So this case also will give us the overflow. If you recall, we studied this in the microprocessor and microcontrollers where we had the overflow in the last semester. So the register file has no longer triggered for part for the pipeline, and at the end of the write back stage, as you can see over here. So the register file over here is not part of the pipeline. We have the other register file which is over here as part of the write back stage. This is why, because now we have 4 stages. So the register file is no longer edge triggered and is no longer part of the pipeline platform at the end of the write back stage. Instead, the register file is latched and written much earlier than the positive edge cycle. This special timing provides that to permit the register file to be written in the first half cycle and read in the second half cycle. So over here, you see this register file, we read in the second half cycle. And here we write in the first half cycle. We talked about this when we talked about the hazards in the previous lecture. So in particular, in the second half cycle, it is possible to read the data written during the first half cycle of the register file. So the control organization, as you can see, the SH is added to the instruction register. 1 bit for control select, 1 bit MD is extended for 2 bits, and new pipeline platform SH is expanded to 2 bits. Okay, new control logic for the program counter is added, and MUX-C has a new selector for the program counter. Now for the program counter, MUX-C is controlled by BS and PS. As you can see here, if it is 0, 0, then increment the program counter. If it is 0, 1, then branch, and PS is 0, then branch on 0. If it is 0, 1 and 1, then it is branch on non-zero. 1, 0, it's jump to the contents of RAA, and 1, 1, it's an unconditional branch, as we said over earlier in the instructions. So as you can see, we have 0, 0, 0, 1, 1, 0, and 1, 1, and it's quite simple to implement this circuit. As you can see over here, this is the circuit that we are talking about. So this is our selector, and this is the RA, BA, and the increment of the program counter. Now, the table for all of the instructions are shown over here. As you can see, all of our instructions are implemented over here with the part 1 and part 2. This is basically our end of this class. So basically, as you see, this is the pipeline. In the next section or the next week, we are going to talk about how this pipeline is implemented and how we solve the hazards when they arise in this pipeline. Thank you for watching. Hope to see you.